All right. So I saw a lot of question on Piazza, guys, and I have something to contribute here. So for the shifting, there are not three things to consider: is the number positive or negative? Okay, and we care about the most significant bit is set, is whether it's set or not before any shifting operation. Okay. Also, the truncation that happened before shifting. Okay, is there truncation in the problem or not? And also, after the truncation, does the most is the most the MSP the most significant bit is set or not? Okay, we're gonna go like this is basically a true table for all of these. We're gonna see each case and how that and how can we get the answer out of that. So let's start with positive. Okay, so we have a positive number. There is no truncation, and the most significant bit is not set. So the most significant bit is not set, yes. So a case like this would be when we have a statement like this. We're taking this number and we're shifting it 1. So remember, guys, this is an odd number, okay? Not negative number, not an even number. So it's just a bit harder because if it was like 2, then it would be it would be easier because it would be like 0 and the 7 will go like this, right? Because this is like 10 to the power of 2. So it means like 4 bits. That means one hexadecimal char to the left. Okay, so let's not get distracted. So here we have this number, which is a positive number. Good. Truncation is not happening, which is what the table is saying. And the most significant bit is set by truncation. This is not applicable because we're not doing any truncation. So how are we going to deal with this shifting? Well, first of all, I would recommend always to do it in binary until you get until you become good at it, and then you can move forward and do it by just hex or by looking. So there we go. Always mark the highest bit. So since this is a 32-bit number, because as soon as you do this, it casts this to a 32-bit and this to a 32-bit number. That's Java. So we have these 4 bytes. This 1 byte is just all 0. This 1 byte is 0, and this is 1 byte all 0. This is A7 and this is A0. Okay, and we're shifting this all by one bit. As you can see, this is a 4-byte number, which is what int is in Java, and also 4 bytes just means 32-bit. We just changed the number, so basically 32-bit over 8-bit times 8-bit on 1 byte. And this will cancel this one. It's 4, right? So you get this 4 byte from 32-bit. Anyways, this is all distractions. Now, we know it's easy shifting. You keep shoving zeros in here, but we only have 1 0 here. So we're just gonna go 0 and then shift everything up. So as a result, we're gonna shift this one out, which is why you have that one out here. This is mid steps. Now let's go to the results. Basically, we just shifted everything. So as you can see, the 7 here and the 0, we start having an E instead, and is 0. So the number is completely changed. We write that in hex, we convert it back to hex. So these become 0, this becomes 0, right? So as we know, every 4-bit is 1 hex number or digit. And char character, yes. Then one more, and one more. Also one more for these gone. And we left up with this, which is E0, okay? This is the first case. Very straightforward. Everybody knows this. The tricky ones will be coming soon, so let's stay tuned for that. All right, what is the second case, Abdul? All right, second case is when it is, it's a positive number, okay? And again, there's no truncation, and the significant bit set. So this case also does not apply. Therefore, there is no example, or if there is an example, it will be similar to the one that we just explained, because this part has no effect in when this changed, right? All right. So what is the third case? Which is, well, you have a positive number. We have a positive number, and then there is truncation, but the most significant bit is not set after the truncation. Okay, give us an example. Well, okay, we have the truncation. The highest bit is not set after truncation. I formulate this number like on purpose, just so we can have that case. And also, yeah, there's truncation, and the number is positive. Okay, so how we translate this? Well, first of all, just highlight the highest, the most significant bit. Since this is a, let's be careful. This is a big Indian, right? If it was little Indian, we'll have to focus on this, and we'll see how that changes everything. I don't think I have an example for that, but this is something to be to consider for exams. Okay. So this is the highest, the most significant bit. For 7, we get, this is 0, 0, 0, 0. I'm writing in hex here. This is 0, 0. This is 7 again. It's like a 111, 7, and 0. So this number I chose on purpose just to show something. That, okay, so because we truncate to byte, that means what Java will do, we'll remove this, remove this, remove this, and choose the first byte, which is 4 bits. 8 bit. 8 bit equal 1 byte. Okay, so Java will just keep this. So basically, we have the final, after the truncation, we have this. And since our example is about that the most significant bit is not set after after truncation, which is what happens here. The most significant bit of this number. So remember that this bit set here is not like this one. In fact, the one that we end up having is this byte, is this bit, is this one. So this is this, not this, okay? Because all of this got truncated when you change it to byte. So say you want these ones, maybe you can shift this way until it's here, and then you do byte truncation, so you can have this by itself, but that's just, you can do that in Java too. Now, back to our example. So we have this now, okay? So now, since the most significant bit is not set, then Java, after it shifts, it just fills everything with the same number, which is 0. So let's look at the final result here. We see that this byte is still the same here. After we shifted, the one have moved to the end of the number, which is like this, which is E again, like the one that we studied at the top. Case number 1, right? This E, that's a 0. These are all zeros after shifting, right? So as you can see, the one that was here been moved to this here, and the one that was here been moved here, and the one that was here moved here. Okay, remember that. You're gonna tell me that the most significant bit set is 1? No, because before shifting, we look at it before shifting, right? What the number was before shifting. Okay, and now after shifting, this is the most significant bit. Should have highlighted that. All right, so this is an example of truncation and the highest the most significant bit after truncation is not set. Let's look at another example where the number is positive and we have truncation before shifting, and also that the most significant bit is set after the truncation. And this is probably the most, the one that confuses students the most. Let's look at an example, and there we go. So here's an example of truncation, positive number, and the highest bit is set after truncation. I know you might not know this by looking at the number, but these again, this is like these stuff I artificially put together so it work in the example. All right. Now let's expand this number into binary so we can see it. All right. So this is a 32-bit number. How do I know that? Because that's by default 32-bit number in Java, right? But if when we do this, it's gonna be 8 bits. But for now, we're just gonna evaluate this. We're gonna write everything. So byte is here, the assignment is here, and then you write out the number. So you get the 0, 0. I'm doing this in hex again, 0, 0, 0, 0. And then here is 8 because this is 0. And then this is 8, right? Binary 8. All right. What else? Now let's apply the truncation. When we do the truncation, we leave the least significant bit. Okay, not the most significant, we keep the least significant byte, sorry. All right, so the least significant byte would be this. So this is what we have here. Now notice something. The most significant bit in the original number was this, was 0. Then we truncated, we got this part. Now, Java only knows about this part. So basically the statement now becoming this. I'm putting the comma here every 4 digit, every 4 binary bit, just so it's easy to see, okay? So now after the truncation, we have the highest bit is set to 1, bit set to 1. This is interesting because now when Java does the shifting, it will have to extend this all with ones so it can keep the highest order, because I think it considers a negative this way, I think. Well, I don't know, I'm just guessing. But anyways, so this number will be repeated all the way until it fills the 32-bit. All right. Okay, let's see the final result. Here we see the 1 is being shifted. So this 1, 1, 2, 3, 4th number went here, right? That's what we have here. And the 0 came in to the group and shoved in. So there you go, it's here. However, all these zeros after the 1 being pushed here, that 1 is being copied all the way to the 32. Okay? And therefore, the most significant bit is becoming the sign of the number. Okay? So definitely this number doesn't look good. This is why you see the F's in the examples that the instructors are giving us. You're seeing these F's, right? And you wonder why. Well, because the number that after cutting the byte, or even before cutting the byte, if it was 1, we're going to see another example where this is actually a 1, right? And we'll have the same effect. So, because this is a 1, and this is number 8, this is why they say if it's 8 or above in the hex, 8, 9, 10, A, B, C, D, and E, and F, you gotta extend the number. But this is a general rule, but there's one exception that I will explain later. And that is just because 8, as you might guys know, we're just gonna do some basic stuff. This is value of 1, this is value of 2, 4, and then 8, right? It's like a 4-bit number. So if this is set, which is the most significant bit after truncating, if this is set, then the number will always be 8 or above, because whatever you add here is going to make it bigger than an 8, right? However, it was 7, then this is going to be 0, and then you have all these other numbers. So 7 and less will not give you the most significant bit as 1, but the rest will give you. Okay, I hope this is clear. first time explaining it. I spend a lot of time writing it. Just first of all, like for myself, and then in case someone else is actually struggling as they did. Anyways, so this just makes it negative number, and then I wanted to get this value, right? So what I did something called choose complement. So in that case, you have to do two things. So let's just do it systematically. 0, 0. So if I believe this number is a negative number because of all the f's, and I want to know the positive of it, so I can just say, let's say it's a positive x, right? And now I'll be like, oh, okay. So since this number is a negative number, I can just say like, oh, it's a negative x. I know that, right? I think I did it with red here because I wasn't sure of my calculation last night. All right. So with this, we're gonna first of all negate. And by the way, if you have an x, if you do the two's complement, you're gonna get negative x. And if you do negative x and you do two's complement, you're gonna get an x. So it works both ways. It's very important. I didn't know that until I start like playing around with these numbers. Now, this is a two complement, and I know that this is a negative number, so I know I'm gonna get the positive out of it. So what? First of all, we negate this. We negate these bits. So this is when you negate this, it gives you an f, and this is an f, right? And negate the f, you get a 0, 0, 0, 0, 0, 0. If you don't know what I'm talking about, just write out the bits. So for a 0, if you negate all of them, you're gonna get 1, 1, 1, and 4 ones is f in hex. Okay, the same way in hex, the same way for f. I mean. All right, so this is the first step. The second step is that we need to add a 1. This is how you do two complements. Now, if you add a 1, f plus 1 or 1 plus f is 10. You get carry 1. It's 16, right? It's 16, and 16 is like 0 here or 1 here. And then this also is 0, and then this is this also a 16, so it's like a 0 in this, and you carry 1 here, and then you get your 1 here. You get 1 on the next bit, and then the rest is zeros. Okay, so this number is 100. So I know this number is a negative number, which is negative x, and I know if I do two complements, I'm gonna get the positive of x. So since this turned up to be, when I did the complement, it turned to be 100, then this number is a negative 100. Okay. So yeah, I think my calculation was correct last night. This is just another wave formula. I think the professors will be okay with this as well, because I don't think we write this notation with a negative in front of it in the class. I mean, I haven't seen it maybe in one clicker or two, but it is what it is, I guess. Okay, so this is one of the trickiest. It's not the most tricky, but one of the trickiest. Now, what if you don't want that high order, the most significant bit to be repeated all the way, all right, like we did in the previous example? In that case, Java provide like another shifting, which is just by 3 errors. So as you can see, it's the same example with the same conditions: positive, truncation before shifting, and then after you truncate, the most high significant bit is set. But just this time with this. Let's see how that affected. Okay, so for 80, we I don't want to go through this again, but we can just go real quick. So 0, 0, 0, 0, 0, 0, 2 zeros, 2 zeros, 2 zeros, 2 zeros, and then here is 8, right? 1,000 is an 8 for this part only, because it's a binary to a hex, and then 8, and then this is A0. Okay, now after truncating, same stuff. We lose the most significant bit as 0, and we just have it 1 now because we only kept this byte. Okay. Now, what we expect after the shift, we expect that this to be repeated, copied to the rest of the 32, to the other bits. 32, yeah. But what happened, Java noticed that, oh, we have another one here. So this is a special notation, so it will do something different. It will repeat it by with 0. It would fill it with 0. So let's see how that turns out to be. So this is our 1. Okay, you see? There you go. Let me put both of them next to each other so we can see. Okay, I hope this is clear in the video. This is the one. It was before at the end of the first bit, but now it's at the beginning of the second byte. It was at the end of the first byte, the most significant bit. Now it's in the least significant bit of the second byte, so it's being shifted once. Okay. However, the repetition here did not happen. See, this filled it all one. This did not fill it with one. So be careful, guys. If you see this in an exam, just do it slowly. Do this. I know you don't want to be in slow in exam, but you might just need to just be careful about that. Write it out. See where you're truncating. Is it one or not? If it's one, repeat it. Unless there's three shifts. It's one shift, but with the 3 errors. All right. Now let's get to the negative numbers. It's tricky. You have a negative number. Okay. You don't have any truncation, and this does not it's not applicable because you don't have truncation to see if the most significant bit is set or not after the truncation. Okay, so negative number. Let's go negative 17 again. It's case number 5. I artificially made this number because I know. No, actually, I lied. I mean, I made it, but I think this is the same as the other example, just in negative. Okay, so how did I get this number? I wanted a negative number, and I just wanted to, if I shift it. It's just the same example. So how do I know how to write this in binary? I do 70 in binary. And boy, let's do this. So, actually, I have 70 somewhere else. Okay, so this is 70. We flip all the bits. We flip all these bits to 1, 1, 1, 1, 1. And then this one, we flip it to 1, 0, 0, 0. And this one, we flip it to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 to the end, right? But after that, I'm just going to do it. I want this video to have the essential knowledge for everybody. So 1, 1, 1, 1, 1, 1, 1, 1. Okay, 1, 1, 1, 1. 1, 1, 1, 1, 1, 1, 1. I got bored. And then this is, I'm just negating here. So you guys let you know. So now we are here, and then this is 1, 0, 0, 0. It's boring to do binary, but for the sake of the video, we're going to do it. Okay. To do that, now we need to add 1 to get it 2 complements. Why we need 2 complements? Because this number is in 70, and I want the negative 70 out of it, just to prove that to you how I got this number. Okay. Alhamdulillah. All right. So where we at? Yes, so let's add number 1 to it. If we add 1 to this, I think I should have just done it in hex. I guess, yeah, it's easier for me to do it in hex. So 0, 0, 0, 0 for this, 0, 0 for this. Oh, I'm negating, so, okay, yeah. So 0, so this part for 0 is just going to be 0, right? So if I negate it, this is going to be an F, because I'm just going to set all these set bits to 1. So we get FF, 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 and then this one is, yes, this one is going to be 1, 0, 0, 0, which is an 8 in hex. This is 0, you negate it to F. Wait, 1, 0, 0, 0, yes, 8. Okay. Now I want to add a 1. There you go. So if you add these, you're going to get a 0 here. You're going to carry off 1. 90 FF. So now you know that this is a negative of the 70. Now let's see. FFF and 90. Let's see if that's what we have down here. Well, yeah, this is a 9. And this is 0. And all of these are Fs. Okay, so basically I'm just proving that this is a negative 70. Not that it matter, but just needed a way to that if you want to create, like, say, a number to test things with, you know how to create it. You create the negative number that you want, and then you have the two complements to know what is the positive version, and then maybe you write it here. Okay? All right. So again, there's no truncation, so we get this number, and then we want to do, we will just shove a 0 here, and shift by 1, and see how that affects the whole thing. It does not affect it much, but it just give a different number. So you see this pattern, 2 0s 1 1. Here we have it here. So that means they're shifted, right? Shifted for 1 bit. Usually I think our shifting would be positive. I mean, sorry, it's a multiple of 2 just for easier calculation, but I just needed to go 30 here. Okay, let's just simplify this number. We realize it's this, FFs, and then A20 now became a 20 here, right? Sorry, this is a 2, this is a 0, so in X it's 20. All right, if you do again the 2 complement of this number by flipping it all, negating all these numbers and then +1, you realize that this is a positive, easier. Therefore, the number that you converted from the took its 2's complement, it's a negative number. So, all right. I believe we have 2 more cases. Okay, the last case is the tricky one. This case is not applicable because if you don't have truncation, again, you won't have this case. I mean this. I'm talking about number 6. Okay, now let's do number 7. So you have a negative number. You have a truncation. Okay, but the highest order bit is not set. Okay, so excuse me. Okay, how do I know this? I just created the number first. I made it the way I want for this case, and then I find out that it's negative 90. So this is the number, negative 90, and there before truncation, here it is. Then after you do the byte, how do I know 90? This is 9, this is 0, and the rest is F. Okay, or you can just, again, negate this number, take the +1, and then you see the number, and you read it is going to be like 90. So you know that this was a negative 90. Okay, so after truncation, you realize that we only have this. Okay, the most significant bit was 1, but now it's 0. You see? So this is a positive number for in Java's eyes, right? This is why you gotta be careful when you truncate. It's a funny operation. So here it was a positive and then turned out to be 0. It was a 1 negative, and then turned out to be a 0. It's the same situation as what we had here. We had it like it was a positive number. It was a 0 and then turned out to be 1. 0 and then turned out to be 1, right? So truncation is tricky. 1. Okay. So here it was originally a 0 and a 1 and then became a 0. Okay. So what do you guys think? What do you guys think would happen after this? Well, definitely this will be repeated, right? Because this is what Java does. When you have this truncate, when you have this this operation, it will just take the most significant bit of the number that you're currently dealing with, whether it's truncated or not. You're just gonna, where's the most significant bit, and you just repeat it. I would have to ask the professor about having Little Indian, where it's the opposite, right? You have the 1 here, but don't worry about it now. We should ask that in Piazza. Okay, this is our byte. Let's see after shifting those 3 numbers with the 0, probably they're gonna just end up being somewhere else. Yeah, there you go, shifted 1. However, did you guys notice something? Our most significant bit is here, and it's just being repeated. If this was also a 3, it would just put the zeros, but those zeros, if this was a 3, after this will be zeros, but there will not be copy from this, but it will be like a 0 because of this. Hope this is clear. If not, just go back to the example where we did the 3 shifts at the top, and hopefully that will clear. be clear for you. Okay, so this is the number, and then we just translate this number to see what this is. We realize that this is an E, and this is a 0, so our number is this. So we turn up to be having a positive number. Okay. So, and it will be the same if we do the 3, right? Because just in this case, it's the same. What else? Well, last case, which is you have a negative number, you have a truncation. However, after the truncation, the most significant bit after the truncation of that byte is set to 1, basically, set to 1. Let's see how that is. Okay, so we have a number, a truncation, a negative number, and we're shifting it. Notice, guys, this will break the rule, because you remember the rule is like, oh, if it's above 7 or less, you no sign changing. No F's, and then if it's 8 or bigger, just put F's, fill it with F's. We'll see this is not the case because of this sign, okay? Because of this sign. Gotta be careful in the exam. I want every one of you want to get like 100% on this, on these type of questions. And hopefully this comes in a timely manner before the quiz. Actually, the quiz is released today, so I hope you didn't take your quiz yet. Okay, let's write this number out. Well, this number would be like this. How do I know? Well, I did the 70. I did the negation. All right, I got some number, and then I added 1 to that number, and it gave me a weird number, which is this one. So I know that this is negative 70, and then I wrote it here. It's just me finding out how to write a certain number. Okay. I know this is taking too long, but be patient, almost done. So the most significant bit is set. We truncate. There you go. We are here. The most significant bit is set, but it's not set from here. It's not the same. This has been truncated. All of this, it's this. Okay. Now, if we shift, we're going to get this to be repeated, right? Although the number is negative 70, but yes, we was set. Okay. And yes, this is what happens. I just want to highlight these are these because it's like just been shifted for 1. Okay. But again, the 1 byte is just being repeated, the most significant bit. Not here, but from here. It was the highest significant bit here. All right, so here you're just shifting and copying. Okay, so the tricky part about this is that this is a 7, but also got caused us to copy 1s over. Okay, so some notes. Shifting might happen before casting to bytes. So all the rules that we just said is that like it was a byte, and then from the byte we had a number, whatever that number is, and then we shift it. So be careful, guys, because you might get a different one, which is like, shifted to 2, and then all of this casted to a byte. That's what I mean. Okay, the order matters. Now, and also be careful if something like this happened. Right? I don't know which will take precedence. Is it the casting first or this? I'm not sure. So you can just try it in Java and see it on the browser. Okay. Java editor. These covering that we just did just covers the left shifts, the right shifts. I would assume they're the same. They're like just filling. Take the most significant bit and just fill it with whatever the most significant bit is, and repeat it with 0 is 0, 1 is 1. But maybe you need to double check that. And yeah. Okay. Usually they give even shifts, but odds of shifts is possible as well. No, we just covered the odd ones. If you do the full binary, you are safe. Just but a bit slow. So all right. I hope this helps, and thank you so much.